There is a night coming that makes every other night in the history of the cosmos look like a brief spark held against an infinite darkness. A night so total, so complete, so absolute and unbroken, that the word darkness does not come close to capturing it. Not the darkness of a power outage, not the darkness of deep ocean trenches where no sunlight has ever reached, not even the darkness of interstellar space as it exists right now, still faintly lit by the ancient afterglow of a billion suns scattered across the visible universe. This coming darkness is something else entirely. It is the darkness that settles in when the last sun has radiated its final photon and gone cold. When the last glowing ember of a white dwarf, cooling over trillions of years, finally drops below any temperature worth naming. When the black holes that inherited everything, those supposedly eternal engines of gravity, have quietly, almost apologetically, dissolved themselves into nothing through a process so slow and so gentle that no one in the universe could have noticed it was happening until the very end. That night is coming. The laws of physics guarantee it with the same certainty they guarantee that ice melts in a warm room and that a pendulum eventually stops swinging. The question is not whether it will arrive. The question, and this is the one that has kept some of the sharpest minds in theoretical physics up at night, is what, if anything, comes after it. That question sounds almost circular at first. After the universe ends, surely there is nothing. After is a word that requires time, and if the universe is genuinely over, time has no stage left to play out on. But the deeper you look, the more you realize that the question is not as empty as it first appears, because the universe does not end the way a campfire ends, burning fiercely and then going out. It ends slowly, in stages, over timescales so vast they make the entire current age of the cosmos look like the opening fraction of a second. And at each stage, things happen, strange things, improbable things, things that the laws of physics permit and in some cases demand, even in conditions of near-total emptiness and near-total disorder. And beyond the last of those stages, at the furthest edge of what our current theories can describe, some of the most serious cosmologists alive are genuinely, rigorously, with full mathematical machinery, proposing that the story does not simply stop, it transforms, it continues, or it begins again. So get comfortable. Turn the lights down if that feels right. We are going all the way to the end of everything, and then we are going to keep walking. Part 1. The Age We Live In, and the Last Stars. Right now, the universe is doing something it has never done as brilliantly before, and will never do as brilliantly again. It is making light. Every direction you look from the surface of the Earth, the sky carries the output of nuclear furnaces so powerful that a single average one of them converts 600 million tons of hydrogen into helium every single second, simply to maintain its equilibrium against its own crushing gravity. The Sun has been performing this conversion for roughly 4.6 billion years. During that time, it has consumed hundreds of Jupiters' worth of hydrogen and turned them into helium and heat and the light that powers every living thing on this planet. It will continue for approximately another 5 billion years before the hydrogen in its core runs out, at which point it will swell into a red giant large enough to engulf the current orbits of Mercury and Venus and possibly Earth, then shed its outer layers into a glowing planetary nebula and leave behind a dense, Earth-sized remnant called a white dwarf. That white dwarf will cool, slowly, over billions and then trillions of years, radiating its stored heat into an empty, expanding universe until it goes cold. That is the fate of an average star. But the universe contains stars of all sizes, and the smaller ones live much, much longer. Astronomers call the smallest full hydrogen-burning stars red dwarfs, and they dominate the stellar census in a way most people do not realize. Roughly 70 to 75% of all stars in the Milky Way, and in the universe generally, are red dwarfs. They are simply too dim to see with the naked eye from Earth. None of the 2,500 or so stars you can see on a clear dark night being a red dwarf, despite the fact that there are more red dwarfs in our galaxy than every other kind of star combined. Red dwarfs range in mass from about 7.5% to roughly 50% of the Sun's mass. This modest mass means their cores are under lower pressure and less hot, meaning fusion proceeds far more slowly and gently. A red dwarf with half the Sun's mass will burn hydrogen for roughly 56 billion years before running out. A red dwarf near the very bottom of the mass range, just barely above the threshold required to sustain hydrogen fusion at all, might burn continuously for over 10 trillion years. 10 trillion years. The universe is currently 13.8 billion years old. 10 trillion years is more than 700 times the current age of the cosmos. These stars are misers of unimaginable patience, hoarding their fuel across spans of time that dwarf all of recorded history and geology and evolutionary biology combined, multiplied by a number that makes the head spin. And unlike sun-like stars, which burn only the hydrogen in their central cores and eventually run out even with reserves in their outer layers still untapped, red dwarfs are fully convective. They stir themselves continuously, mixing their interiors the way a spoon stirs a cup of coffee, ensuring that fresh hydrogen from the outer layers is constantly being cycled into the core for fusion. They use nearly all of their hydrogen before running out. When a red dwarf finally exhausts its fuel, it does not explode or swell dramatically. It simply cools and dims, slowly and quietly, eventually passing through a theoretical phase called the blue dwarf, a stage that has not yet been observed in the real universe, because no red dwarf has had enough time to reach it, and then cooling further into a cold, dark, inert ball of carbon and oxygen, roughly the size of the Earth, but with a mass close to that of a star. The astrophysicists Fred Adams and Gregory Laughlin, in a series of landmark papers published in 1997 and then collected in their 1999 book The 5 Ages of the Universe, formalized the timeline of the universe's future using a logarithmic scheme they called cosmological decades. They defined the nth cosmological decade as 10 to the n years after the Big Bang. Right now, we are living in approximately cosmological decade 10, meaning the universe is roughly 10 billion years old. The era of stars, what Adams and Laughlin called the stelliferous era, meaning the star-filled era, spans from roughly cosmological decade 6 to cosmological decade 14. That is the range from about 1 million years after the Big Bang to about 100 trillion years after the Big Bang. We are in the middle of the stelliferous era, not at the beginning, not near the end, somewhere in the bright, living heart of it. But the peak of star formation is already behind us. The universe made stars most vigorously about 8 to 10 billion years ago, when the interstellar gas was denser and more abundant, and galactic mergers were more common, and the conditions for star-forming molecular clouds were more frequently met. The rate of new star formation has been declining since then, slowly, steadily, like the attendance at a party in its final hours. There is still plenty of gas left, particularly in the outer disks of spiral galaxies like the Milky Way, and new stars will continue to form for a very long time to come. But the trend is firmly downward, and it will not reverse. Roughly 100 trillion years from now, the last red dwarf anywhere in the universe will consume the last of its hydrogen and quietly begin its transition to a cold, dark ball. No new stars will form after that, because the diffuse clouds of gas that collapse to form stars will have been exhausted. The reservoirs of raw material that fed the stelliferous era for over 100 trillion years will be emptied. The galaxies will still exist, their shapes still familiar from the outside if you could somehow watch them. Vast spirals and ellipticals populated not by shining stars but by stellar ghosts, white dwarfs and neutron stars and black holes and cooling brown dwarfs and frozen planets, all orbiting each other in the ancient gravitational patterns they established when the light was still on, but generating nothing bright enough to see from the outside. Picture that sky, not the sky over your head tonight, crowded with the light of 2,500 visible stars and the diffuse glow of the Milky Way stretching overhead. The sky at the end of the stelliferous era, every star gone cold, every galaxy dark from the inside. The universe populated by vast networks of dead and cooling objects drifting in silence through expanding space. The cosmic microwave background, the faint afterglow of the Big Bang that currently fills all of space at 2.7 degrees Kelvin, would have cooled further, redshifted by the continued expansion of the universe to even longer wavelengths and lower energies. The universe would be a few tenths of a Kelvin, a few thousandths of a Kelvin, somewhere in that range of cold that has no human reference point. But this deep silence would not last forever unchanged, because the objects drifting through that darkness are made of matter, protons and neutrons locked in atomic nuclei, held together by the strong nuclear force, surrounded by electrons and arranged into atoms and molecules and crystals. And matter, as it turns out, has its own slow drama left to play out, a drama that unfolds on timescales so vast that the entire 100 trillion-year life of the Stelliferous era looks like a brief morning before an eternity of days. Before we go further, drop a comment right now and tell us where you are in the world and what time it is for you. There is something worth marking about watching a video on the end of everything, from whatever ordinary corner of the universe you are in right now. And if you are new here, and this kind of thinking is your kind of thinking, subscribing takes about 2 seconds, and it means the next one finds you automatically. Part 2. The Degenerate Era, when matter itself begins to dissolve. The death of the last star does not mark the end of the universe's structure. It marks the beginning of what Adams and Laughlin called the Degenerate Era, a period that spans from roughly cosmological decade 15 to cosmological decade 37. That is from about 1 quadrillion years to something in the neighborhood of 10 to the 37th years after the Big Bang, a number with 37 zeros, a number so large that if you wrote it out in standard notation, the zeros would fill several pages of paper. These are the years when the universe's main population consists of objects that ordinary physics labels as dead, but that are, in a deeper sense, still alive, with the humming tension of quantum mechanics holding their matter together against the relentless pull of gravity. White dwarfs are the most numerous of these remnants. When a star like the Sun reaches the end of its hydrogen-burning life and expels its outer layers as a planetary nebula, the dense core that remains is a white dwarf. This object, roughly the size of the Earth but with the mass of the original star still compressed within it, is composed primarily of carbon and oxygen nuclei surrounded by a sea of free electrons. Nothing is fusing inside it. There is no nuclear fire. It simply sits there, held up against gravity, not by any form of energy production, but by electron degeneracy pressure, the quantum mechanical resistance of electrons to being crowded into the same quantum state. The Pauli exclusion principle, which arises from the half-integer spin of electrons, prevents those electrons from all occupying the lowest energy configuration, and this resistance generates an outward pressure that holds the white dwarf in perfect balance against gravity, even without any ongoing fusion. This is remarkable when you sit with it. The floor beneath your feet right now is solid, not primarily because of the chemical bonds between atoms, though those matter too, but because the electrons in those atoms resist occupying the same quantum states as the electrons in other atoms. The quantum nature of spin is what keeps your hand from passing through the table when you push on it, and white dwarfs extend this same principle to an object with the mass of a star. They are quantum mechanical in the most fundamental sense. White dwarfs cool very slowly. With no energy source, they can only radiate away the thermal energy stored in their ions, and there is a lot of it, released over the course of the star's billions of years of fusion. The coolest and oldest white dwarfs detected in the Milky Way are around 3,000 to 4,000 Kelvin, barely warmer than a candle flame, after roughly 10 billion years of cooling. Calculations suggest that a white dwarf cools to black dwarf temperatures indistinguishable from the cosmic background, on a timescale of somewhere around 1 quadrillion years, the beginning of the degenerate era. After that, they are simply cold, inert spheres of carbon and oxygen sitting in the dark. Neutron stars are the remnants of more massive stars. When a star between roughly 8 and 20 solar masses exhausts its fuel and its core collapses catastrophically in a supernova explosion, the core forms a neutron star, an object roughly 20 kilometers across, that packs 1 to 2 solar masses into a sphere. Neutron stars are held up against gravity by neutron degeneracy pressure, the same Pauli exclusion principle applied to neutrons rather than electrons. Their density is extraordinary. A teaspoon of neutron star material would weigh roughly 10 million tons on Earth's surface. A cubic centimeter of neutron star contains as much mass as an entire mountain range. Brown dwarfs occupy the other end of the mass spectrum, objects that formed through the same process as stars, the gravitational collapse of molecular cloud cores, but that never accumulated enough mass to sustain full hydrogen fusion in their cores. They smolder for billions of years through a lesser form of fusion involving deuterium and in some cases lithium, then cool slowly into cold, dark objects drifting through space. Their lifetimes are shorter than red dwarfs, but their eventual fate is similar: slow cooling into cold balls of gas, and eventually, if proton decay occurs, slow dissolution into radiation. Now, the critical question of the degenerate era, the question on which the entire subsequent history of the universe's matter depends, is whether protons decay. A proton, the positively charged particle in the nucleus of every atom from hydrogen to the heaviest element on the periodic table, is extraordinarily stable by any everyday standard. It has been sitting inside nuclei since the first few minutes after the Big Bang, roughly 13.8 billion years ago, and has shown absolutely no sign of spontaneously falling apart. Its measured lifetime places it at greater than 10 to the 34 years for specific decay modes, a lower bound set by experiments like the Super Kamiokande detector in Japan, a massive tank of ultra-pure water deep underground, surrounded by photon detectors, watching for any faint flash that might indicate a proton spontaneously disintegrating somewhere in the 50,000 tons of water. No such flash consistent with proton decay has ever been detected. But many theoretical frameworks in particle physics, particularly the grand unified theories that attempt to describe the electromagnetic, weak nuclear, and strong nuclear forces as different aspects of a single underlying interaction at very high energies, predict that protons are not perfectly stable. They have an extremely long but finite lifetime. Most such theories predict lifetimes somewhere between 10 to the 34 and 10 to the 40 years, with the precise value depending on which specific grand unified theory you believe and which decay mode you are looking at. The experimental constraint from Super Kamiokande and similar experiments has already ruled out many of the simplest grand unified theories, but more complex versions with longer predicted proton lifetimes remain viable. If protons do decay, the degenerate era ends not with any external catastrophe, but with a quiet internal dissolution. White dwarfs, neutron stars, frozen planets, the rocky material that was once planetary surfaces and asteroid belts, and the solid cores of dead gas giants. All of these objects would slowly, grain by grain, atom by atom, proton by proton, lose their structural substance as the protons within them spontaneously transform into lighter particles. The decay products include pions and positrons, which almost immediately interact and annihilate, producing gamma-ray photons. A white dwarf undergoing proton decay would not go dark immediately. The energy released by proton decay within it would keep it faintly glowing, not through fusion, but through this slow internal disintegration, like a candle that burns not wax but the fundamental constituents of nuclear matter, dimming over timescales of 10 to the 37 or 10 to the 40 years. The last white dwarf would dissolve. The last neutron star, harder and denser and more degenerate than any white dwarf, would crumble. The last frozen planet, the cold, dark remnant of a world that once had oceans and weather and perhaps life, drifting in the dark void, would eventually turn to gamma-ray photons and free electrons and positrons as its atoms fell apart from the inside. Every solid thing, every rock, every crystal, every frozen sphere of water ice that once was a comet in the cold outer system of a long-dead star, all of it, eventually and silently, taken apart not by any energetic external event, but by the same internal quantum probability that governs radioactive decay in an ordinary atom, applied to the proton itself. If protons do not decay, something else still dismantles the degenerate objects, just more slowly. Quantum tunneling processes, operating on incomprehensibly longer timescales, can cause nuclei to gradually convert their material toward more energetically stable configurations. Iron is the most energetically stable nucleus, meaning the atomic configuration that sits at the lowest point of nuclear binding energy. over timescales that make proton decay timescales look brief. Quantum tunneling would cause the carbon and oxygen in white dwarfs to convert slowly toward iron, with the energy difference being radiated away. Eventually, the iron core of what was once a white dwarf would itself be subject to further tunneling processes, and given enough time, even iron nuclei can tunnel into black hole states through a complex series of processes that theoretical physicists have traced out, producing tiny black holes that quickly evaporate through Hawking radiation. Either way, the degenerate era ends with ordinary matter gone. What remains, waiting to inherit the universe from the last dissolving degenerate remnants, is the one structure that neither proton decay nor quantum tunneling can dismantle: the black hole. Part 3. The slow collision of worlds. Galaxies merging before the degenerate era fully takes hold, and partly overlapping with the late stelliferous era, something happens on a shorter but still geological timescale that reshapes the large-scale architecture of the universe. The galaxies themselves, those vast island universes of hundreds of billions of stars, begin to collide, interact, and merge into single massive objects. The universe is not simply growing darker, it is consolidating, pulling its local matter together through gravity, while dark energy simultaneously isolates those consolidated objects from each other forever. We already know that this process is coming, at least in our own region of the cosmos. The Andromeda Galaxy, a spiral galaxy containing roughly 1 trillion stars and sitting approximately 2.5 million light-years away, is the nearest large galaxy to the Milky Way and the most distant object visible to the naked eye on a dark night. A faint, elongated smear of light, about 6 times the diameter of the full moon in the sky, but almost too dim to notice unless you know where to look. Andromeda is approaching the Milky Way at about 110 kilometers per second. This is not new information. Astronomer Vesto Slipher measured Andromeda's blue shift in 1912, making it one of the first galaxies whose motion was measured spectroscopically, and astronomers have known since then that Andromeda is falling toward us. For many decades, the conventional wisdom was that Andromeda and the Milky Way were on a direct collision course and would merge in roughly 4 to 4.5 billion years. More recent work, combining high-precision measurements from the Hubble Space Telescope and the European Space Agency's Gaia satellite, has introduced genuine uncertainty into this timeline. A 2025 study led by astronomer Till Sawala, published in Nature Astronomy, ran 100,000 computer simulations using the best available positional and velocity data for the Milky Way, Andromeda, the Triangulum Galaxy, and the Large Magellanic Cloud. These simulations found that there is roughly a 50-50 probability of a collision between Andromeda and the Milky Way within the next 10 billion years. In about half the simulations, the galaxies pass within 500,000 light-years of each other, close enough for dynamical friction between their dark matter halos to gradually drain their orbital energy and eventually pull them together, though over a longer timescale than previously thought. In roughly the other half of simulations, the galaxies do not come close enough for dynamical friction to work effectively, and they continue their orbital relationship for much longer. The presence of the Large Magellanic Cloud, a large satellite galaxy of the Milky Way, whose effects were not fully accounted for in earlier calculations, turns out to pull the Milky Way off the orbital plane that would carry it directly toward Andromeda, reducing the likelihood of a near-term close encounter. What does not change regardless of the exact timing is this: the Milky Way and Andromeda are gravitationally bound to each other and to the rest of the local group, the collection of perhaps 50 or more galaxies that share our cosmic neighborhood, dominated by the Milky Way and Andromeda, but including several dozen smaller satellite and dwarf galaxies. Dark energy will push distant galaxy clusters beyond the observable horizon permanently, but it cannot overcome the gravitational ties within the local group. Those galaxies are bound to each other for the remaining life of the universe, and eventually all of them will merge into a single massive elliptical galaxy. Astronomers have taken to calling this future object Milkomeda, though the actual name of the object, if any beings were around to name it, would be earned fresh at the time of its formation. The physical process of 2 spiral galaxies merging is not the explosive catastrophe it might sound like from the description. Stars inside a galaxy are separated from their neighbors by distances measured in light years, which on a human scale translates to tens of trillions of kilometers. If you imagined each star in the Milky Way scaled down to a grain of sand, the nearest neighboring grain of sand would still be separated from it by roughly 30 kilometers. Two groups of sand grains separated by 30 kilometers between each grain do not really collide when you drive them together. The grains pass through each other, and the probability of any two individual grains meeting is essentially zero. This is also true of galaxies. The stars in the Milky Way and the stars in Andromeda will not collide with each other when the two galaxies merge. The probability of stellar collision during a galactic merger is negligible. What does happen is gravitationally extraordinary. Tidal forces from the approaching galaxy distort both spiral disks into wild, spectacular shapes. The flat rotating disk of the Milky Way, currently perhaps 100,000 light-years across and relatively stable in its structure, would begin to warp and stretch as Andromeda's gravitational influence grew stronger. Great arcs of stars, ripped from their regular orbits by tidal forces, would stream out from both galaxies in long curved bridges of light. Computer simulations of this process are among the most visually striking outputs of modern computational astrophysics, showing the two spiral galaxies approaching each other and then deforming each other's structure in slow motion over millions of years, wrapping around each other in a gravitational dance before eventually spiraling inward and merging their cores. The gas and dust compressed by the collision would trigger massive bursts of new star formation. Regions of the merged galaxies would blaze with the light of millions of young, hot blue stars, born from clouds of gas colliding and compressed in the turbulence of the merger. The night sky during this period, if there were beings on Earth to observe it, would transform over millions of years. Andromeda, currently a barely noticeable elongated smudge in the constellation Andromeda, would grow larger and larger in apparent size, a galaxy stretching across more and more of the night sky as it approached, growing brighter as its stars compressed and ignited in new formation bursts, until it filled the sky with a sprawling, irregular structure that would make the current Milky Way band seem modest by comparison. The two galactic cores, each harboring a supermassive black hole, Sagittarius A, at the center of the Milky Way, with a mass of about 4 million solar masses, and Andromeda's central black hole M31, with a mass of somewhere between 100 million and 200 million solar masses, would spiral toward each other as the merger proceeded. This process takes time, potentially hundreds of millions of years even after the galaxies themselves have largely merged, because the two black holes need to lose orbital energy through gravitational interactions with surrounding stars before they come within each other's direct gravitational influence. Once they do, they would emit gravitational waves as they orbited each other at decreasing distances, a process that would itself eventually bring them into contact and merger. The resulting single supermassive black hole at the center of Milkomeda would be among the largest in the local group. The merged galaxy, Milkomeda, would be an elliptical galaxy, devoid of the spiral disk structure that both its progenitors currently display. Elliptical galaxies form when mergers disrupt the ordered rotation of the disk, replacing it with the random, spheroidal distribution of stellar orbits typical of this galaxy class. They tend to have very little remaining cold gas, meaning they form new stars at very low rates. Milkomeda would be old, full of aging stars, populated increasingly by white dwarfs and red dwarfs as the more massive stars burn out, gradually darkening over the trillions of years of the late stelliferous era and the early degenerate era. Meanwhile, beyond our local group, every other galaxy cluster in the observable universe is doing the same thing. Each gravitationally bound cluster is contracting internally, merging its constituent galaxies over billions and trillions of years, while simultaneously being pushed away from every other cluster by dark energy at an ever-increasing rate. The expansion of the universe, driven by dark energy, will carry all other galaxy groups beyond our observable horizon within 2 to 3 trillion years. After that point, any observer within the local group, including within the merged Milkomeda galaxy, would look out at the night sky and see only blackness in every direction beyond their immediate cosmic neighborhood. All the other galaxy clusters, all the other thousands of groups visible to us today with our telescopes, would have receded beyond the point from which light could ever reach us. The evidence for the Big Bang itself, the cosmic microwave background radiation that fills the sky today, would be redshifted to wavelengths so enormous and energies so low that it would be essentially undetectable. An astronomer living in the universe of 2 trillion years from now would have no way to know, from observation alone, that the universe was larger than a single galaxy. They would observe nothing beyond Milky Way. They might still be able to infer, from the internal properties of their galaxy and the faint remnant of the CMB, that a Big Bang had occurred. But the richness of observational evidence available to us today, the galaxy redshift surveys, the quasar catalogs, the galaxy cluster statistics that allow us to measure the geometry and content of the universe with precision, all of that would be gone, carried beyond the horizon by the expansion. They would be doing cosmology with far fewer data points, in a universe that looked, from the inside, like a very simple and lonely place. And then, as the trillions of years rolled on, and the last red dwarfs began to dim, and the degenerate era settled in, even Milky Way would go dark. Part 4. The Black Hole Era. Last Lights in an Infinite Dark. The Black Hole Era is the strangest chapter in the universe's biography, not because it is full of dramatic events, but because it is full of almost nothing. It stretches from roughly cosmological decade 38 to cosmological decade 100. That is from roughly 10 to the 38th years to 10 to the 100th years after the Big Bang. A googol years at its far edge. A googol is 1 followed by 100 zeros, a number selected by mathematician Edward Kasner's 9-year-old nephew as a good name for a very large number, and later borrowed for the name of a technology company that is now one of the largest corporations in human history. The black hole era lasts for that long. The current age of the universe, 13.8 billion years, expressed in the same terms, is approximately 10 to the 10.1 years. The black hole era outspans the current age of the universe by a factor of roughly 10 to the 90 times. Everything that happened during the stelliferous era, all 100 trillion years of stars and galaxies and planets and the biology and chemistry and whatever else the cosmos contained, takes up less of the total duration of the black hole era than the first microsecond of your life takes up of the total duration of the universe so far. The objects that dominate the black hole era are black holes, and they are doing something that most people intuitively believe black holes never do. They are evaporating. This process is called Hawking radiation. Stephen Hawking proposed it theoretically in 1974, in what most physicists consider one of the most important single results in the history of the field, a result that required taking both quantum mechanics and general relativity simultaneously seriously, in a regime where nobody had previously tried to apply them both at once. The argument is subtle and builds on the behavior of quantum fields near the event horizon of a black hole. In quantum field theory, the vacuum of space is not empty in any simple sense. It fluctuates constantly with virtual particle pairs, particle and antiparticle flashing into existence and almost immediately annihilating each other back into nothing. This happens everywhere, in every region of space, all the time. It is a fundamental feature of quantum fields, a consequence of the uncertainty principle that allows energy to be borrowed briefly as long as it is repaid quickly. These virtual pairs are not detectable in ordinary space because they vanish before any measurement can catch them. Near the event horizon of a black hole, Hawking recognized, something unusual can happen to these virtual pairs. If a pair nucleates very close to the horizon, one member of the pair might fall inside while the other escapes outward. The particle that falls inside cannot come back out. The particle that escapes outward no longer has a partner to annihilate with. It becomes a real particle, permanently. It carries away real energy. That energy, Hawking showed, must ultimately come from the gravitational field of the black hole itself, meaning the black hole loses mass with every particle that escapes this way. The black hole radiates, not through conventional thermal processes, but through a quantum effect at its horizon. The temperature of this radiation is inversely proportional to the black hole's mass. Small black holes are hot and radiate powerfully. Large black holes are extremely cold and radiate at an almost imperceptible rate. The Hawking temperature of a solar mass black hole, a black hole roughly 3 kilometers across, formed from the collapsed core of a massive star, is approximately 10 to the negative 8 Kelvin, 100 millionths of a degree above absolute zero. For comparison, the cosmic microwave background currently fills the universe at 2.7 Kelvin. This means that every black hole in the current universe is absorbing far more energy from the CMB than it is emitting through Hawking radiation. Black holes in the current universe are growing, not shrinking, because the universe is still hot enough relative to their Hawking temperatures that the energy bath surrounding them overrides the evaporation process. Only when the universe has cooled sufficiently, through continued expansion, to drop below the Hawking temperature of a given black hole will that black hole begin to lose mass in net terms. For a solar mass black hole, that crossover point is still extraordinarily far in the future. A stellar mass black hole will take approximately 2 times 10 to the 67th years to fully evaporate through Hawking radiation, a duration that is already 10 to the 57th times longer than the current age of the universe. A supermassive black hole with the mass of a large galaxy, perhaps containing material equivalent to 10 to the 11th solar masses, will take closer to 10 to the 100 years to fully evaporate. That is the Google years we mentioned. The most massive black holes in the universe last almost until the end of the black hole era itself. What happens at the end? As a black hole loses mass, it shrinks. As it shrinks, its Hawking temperature rises. As its temperature rises, it radiates more energetically. As it radiates more energetically, it loses mass faster. This positive feedback loop accelerates. For most of a black hole's lifetime, evaporation is so slow that calling it imperceptible is an understatement. But in the final stages, when the black hole has shrunk to a very small size, the temperature rises sharply and the evaporation rate accelerates dramatically. The last fraction of a second of a black hole's existence is not a quiet fade, but a sudden burst of intense high-energy radiation, a brief, brilliant flash of gamma rays and other particles erupting from the point where the black hole used to be, and then nothing. The flash ends. The space that contained the black hole is empty. No singularity, no gravitational field, no horizon. The black hole is simply gone. The black hole era is populated by these brief terminal flashes scattered across an incomprehensible span of time. Smaller black holes, those formed from individual stellar collapses in the early universe, go first, evaporating relatively quickly. Larger black holes formed from stellar mergers and galactic center accumulations last longer. The largest supermassive black holes, the behemoths at the centers of massive galaxy clusters that have been feeding for billions of years on infalling gas and stars and smaller black holes, last until near the end of the era. For the vast majority of the black hole era, from any given vantage point in space, nothing is visible. Occasionally, perhaps once every unimaginable stretch of time, a brief burst of Hawking radiation signals the final evaporation of another black hole somewhere in the void. Then silence again for another span that makes the wait between events look brief. The universe during the black hole era is not completely dark, but it is about as dark as anything can be, while still technically containing light. The flashes of final Hawking evaporation are the only events worth noting. The universe has, for all practical purposes, stopped, and yet the laws of physics are still operating. Quantum fields are still fluctuating. Space is still expanding. The de Sitter horizon is still emitting its faint thermal radiation at a temperature of roughly 10 to the negative 30 Kelvin. The universe is not dead yet. It is just waiting, in the deepest patience that physics allows, for the last black hole to finish its work. And then it does. The last black hole, somewhere, at some moment that no clock in the universe has kept track of for longer than it can comprehend, emits its final burst of radiation. A flash of particles and photons, expanding outward at the speed of light through an empty, cold, dark cosmos. The flash is gone, almost before it begins. A brilliant but brief end to the last organized structure in the universe. And when it fades, what remains is the dark era. Part 5. The Dark Era, the universe at perfect rest. The Dark Era begins at roughly cosmological decade 100, when the last black hole has evaporated, assuming proton decay has already dissolved all ordinary matter during the degenerate era. It then stretches outward through time indefinitely, not for a trillion years, not for a Google years, indefinitely. As far as the laws of physics as we currently understand them permit, the Dark Era lasts forever. After the last black hole evaporates, the universe consists of what astrophysicist Fred Adams described in stark and almost poetic terms: a diffuse sea of electrons, positrons, photons, and neutrinos. These particles, the final debris of all the matter and radiation that ever existed, are so spread out by the expansion of the universe that their average density is essentially zero. A photon emitted from a black hole evaporation in one corner of the observable universe will travel for longer than the universe's current age before encountering any other particle. The electrons and positrons drift in isolation, separated by distances many orders of magnitude larger than the current observable universe. Meaningful interactions between particles are extraordinarily rare. The photons themselves are in a sorry state. Every photon has been redshifted by the expansion of the universe, stretched by the growing distances between points in space, its wavelength growing longer and its energy falling lower with each passing moment. Photons that were once gamma rays are now X-rays. Photons that were once visible light are now infrared, then microwave, then radio, then something at wavelengths so long they carry essentially no energy at all. The universe in the Dark Era is filled with photons of extraordinary wavelength, their oscillation period longer than many times the current age of the universe, carrying so little energy that no physical process can extract useful work from them. They are, for all physical purposes, indistinguishable from the quantum vacuum. This is the heat death, not a dramatic end, but a smooth, quiet arrival at perfect equilibrium. The second law of thermodynamics, which states that the entropy of a closed system always increases or stays constant, has been fulfilled at last. The entropy of the universe is at its maximum. Every corner of space has the same temperature. No temperature gradient exists anywhere. No free energy remains anywhere. No process that could extract work from any difference in energy or temperature or concentration is possible, because there are no differences left. The thermodynamic arrow of time, the direction from past to future that we experience as the one-way flow of events from organized to disorganized, from hot to cold, from ice to melt water, from complex to simple, has lost its meaning in the Dark Era. There is nothing to mark the passage from one moment to the next, because nothing changes from one moment to the next. The laws of physics still permit a time coordinate to exist. The mathematical variable t can still take increasing values, but the physical content of those values is empty. The universe at one moment is identical to the universe a trillion years later, which is identical to the universe a Google times a Google years after that. Time passes, but nothing happens. The universe is, in every meaningful sense, at rest. Or is it? Here is the turn in the story that most people do not expect, and that some cosmologists consider one of the most profound implications of taking the heat death seriously over infinite time. The equilibrium of the Dark Era is not a state of perfect mathematical zero activity. It is a state of maximum entropy, which is not the same thing. Even in a universe at thermal equilibrium, quantum mechanics permits fluctuations. Not large ones, not often, but statistically inevitable ones, over infinite time. The quantum vacuum is not still. It hums, at the deepest level we have access to, with the same virtual particle activity that drives the Casimir effect and the Lamb shift, and the vacuum energy measured in the cosmological constant. In a universe at maximum entropy, with infinite time ahead of it, those fluctuations are the only story left to tell. They are sparse, they are brief, they are extraordinarily rare. But they are not zero. And in infinite time, anything with non-zero probability must happen. This is the door into the strangest part of the universe's afterlife. Part 6. The Big Rip. The universe that does not wait. Before we explore what happens in the infinite darkness of the dark era, we should acknowledge an alternate trajectory, one that many physicists consider less likely than heat death, but that cannot be ruled out by current observations. It is the possibility that the universe does not quietly cool to equilibrium over a Google years, but is instead violently, totally, absolutely destroyed in a much shorter time frame through a process called the Big Rip. Everything in the story of the degenerate era and the black hole era and the dark era rests on a single assumption about dark energy. It assumes that dark energy behaves like Einstein's cosmological constant, a fixed, uniform energy density that fills space equally everywhere and does not change with time. If this is correct, the universe will expand forever at an accelerating rate, but the acceleration rate itself remains more or less constant. The expansion, while it eventually separates all galaxy clusters from each other, is not strong enough to disrupt structures held together by local forces. Galaxies remain intact, solar systems remain bound, atoms remain atoms. The universe dims slowly, and the remaining objects decay through their own internal quantum processes over the timescales we have been discussing. But dark energy might not be constant. It might be what physicists call phantom energy, a form of dark energy whose density actually increases as the universe expands. The behavior of dark energy is characterized by a parameter physicists call W, which represents the ratio of dark energy's pressure to its energy density. A true cosmological constant has W equal to exactly -1. Phantom energy has W less than -1. Observational measurements place W at around -1.028. Though the uncertainties in this measurement are large enough that a value of exactly -1, the cosmological constant value, remains fully consistent with the data. The difference between W equals -1 and W equals -1.028 sounds trivially small, but if it is real, the consequences are not trivial at all. If W is even slightly less than -1, then dark energy's repulsive effect grows over time rather than staying constant. As the universe expands, the density of phantom energy per unit volume of space increases, rather than staying constant as it would for a true cosmological constant. This means the repulsive force driving expansion becomes stronger as expansion proceeds, which causes expansion to accelerate further, which makes phantom energy more dense, which causes even stronger acceleration. A runaway process. The expansion rate increases without limit, heading toward infinite speed in a finite amount of time. This is the Big Rip, first formally analyzed by cosmologist Robert Caldwell and colleagues in a 2003 paper. Caldwell's original estimate, based on the observational data available at the time, placed the Big Rip at roughly 20 to 22 billion years from now. Later analyses with more refined data have pushed this estimate out considerably, or questioned whether it occurs at all. But the scenario remains physically viable. The sequence of destruction in a Big Rip unfolds from large scales to small. About 1 billion years before the Big Rip, the repulsive force of phantom energy grows strong enough to overcome the gravitational bonds holding galaxy clusters together. Clusters of galaxies begin to come apart. Individual galaxies drift away from each other faster and faster, accelerating away at increasing rates. About 60 million years before the Big Rip, individual galaxies themselves disintegrate. The gravitational cohesion that keeps 400 billion stars orbiting a common center is overwhelmed. Stars scatter. The Milky Way's spiral structure, which has been maintained by gravitational balance for 10 billion years, tears apart. Stars that were orbiting the galactic center for billions of years are suddenly unbound and moving outward with the expansion. 3 months before the Big Rip, planetary systems become gravitationally unbound. The Earth drifts away from the Sun. The Sun has no more planets. The gravitational ties that held the solar system together for 4.6 billion years, the mutual attraction between the Sun and its planets, are simply not strong enough to resist the phantom energy's growing repulsion at the distance scales of a planetary system. 2 months before the Big Rip, the Sun itself, held together by its own self-gravity, is torn apart. 30 minutes before the Big Rip, the Earth is ripped apart. Its internal self-gravity, the attraction of every piece of the Earth for every other piece, is overcome by the phantom energy expansion at the length scale of a planet. The crust separates from the mantle expands away from the core, and the whole structure expands into a cloud of gas and rock and iron, moving outward in a sphere that grows at an increasing rate. In the final seconds, atomic bonds fail. Molecules come apart as electrons are ripped from atoms. Atoms themselves ionize. The electrons separate from the nuclei. Then, roughly 10 to the negative 19 seconds before the Big Rip, the final moment, nuclear bonds fail. The strong force that holds protons and neutrons together in atomic nuclei is overcome by the phantom energy's repulsion at the subatomic scale. Nuclei disintegrate, protons and neutrons scatter. At the moment of the Big Rip itself, the scale factor of the universe, the mathematical quantity that describes the ratio of any distance in the universe at any time to its value at some reference time, diverges to infinity. Space itself expands infinitely in finite time. The universe ends not in cold silence, but in a simultaneous, instantaneous, absolute destruction of every bound structure that exists. From the largest gravitational assemblies to the interior of the last proton, all in the same moment. After the Big Rip, there is nothing, no matter, no radiation, no structured space-time. The singularity at the Big Rip is a genuine mathematical end, as complete and as final as the initial singularity of the Big Bang was a beginning. There are no Boltzmann brains in the aftermath of a Big Rip. There is no dark era. There is no opportunity for quantum fluctuations to produce anything, because there is no vacuum to fluctuate, no space-time to host a fluctuation. The Big Rip is, if it occurs, a more thorough ending than heat death in every sense. The current best observational evidence, from measurements of the cosmic microwave background by the Planck satellite and from large-scale galaxy surveys and Type 1a supernova distance measurements, places Bohl close to -1 but with substantial uncertainty. Most cosmologists consider heat death more probable than the Big Rip, but the margin is observational, not theoretical, and the question will only be definitively answered by future measurements capable of constraining W to higher precision than current instruments allow. We do not know whether the Big Rip is our fate. We know only that current measurements cannot rule it out, and that if it is, it arrives much sooner and more violently than heat death. Part 7. False vacuum decay. The ending that arrives without warning. There is a third possibility, one that operates on an entirely different logic from either heat death or the Big Rip. It does not depend on the long-term evolution of dark energy. It does not require waiting trillions of years for stars to burn out, or trillions of years for black holes to evaporate. It can, in principle, happen at any moment, at any point in the universe's history, including this one, with no warning detectable in advance by any observation from inside the universe. This is false vacuum decay. The concept begins with the Higgs field. The Higgs field is a quantum field that permeates all of space, and when it was first proposed by Peter Higgs, Robert Brout, François Englert, and Gerald Guralnik in the 1960s, it was considered a mathematical convenience, a way of giving mass to elementary particles in the standard model of particle physics. The Higgs boson, the particle associated with this field, was finally detected at the Large Hadron Collider in 2012, confirming the field's existence and earning Higgs and Englert the Nobel Prize in Physics in 2013. The Higgs field exists in a particular configuration, a ground state, determined by the shape of its potential energy curve. Think of this potential energy curve as a landscape. The Higgs field settles into a valley in this landscape, the lowest energy configuration available to it, and it sits there stably. This ground state determines the mass of the Higgs boson itself and, through interactions with other quantum fields, the masses of all other elementary particles, the mass of the electron, the mass of the quarks, ultimately, the stability of atoms and the chemistry of the universe. But in 2013, measurements of the Higgs boson's mass at the LHC, combined with increasingly precise measurements of the top quark's mass, suggested something disturbing. When physicists used these measured values to calculate the shape of the Higgs field's potential energy landscape, they found that the valley the Higgs field currently occupies might not be the true lowest energy point. There might be a deeper valley somewhere else in the landscape, a true vacuum state with lower energy than the state we currently occupy. If so, our current ground state is not a true ground state. It is a metastable state, a false vacuum. The concept of false vacuum decay was first rigorously analyzed by Sidney Coleman and Frank DeLucia in 1980. Their analysis showed that if the universe exists in a false vacuum state, quantum tunneling can spontaneously cause a small region of the field to transition to the true vacuum. This would nucleate a bubble, a spherical region of space where the Higgs field has settled to its true ground state, surrounded by the false vacuum that constitutes the rest of the universe. Inside the bubble, the masses of all elementary particles would be different from their values outside the bubble, determined by the new, lower Higgs field value. The chemistry of the universe inside the bubble would be utterly alien to anything we know. Atoms as we know them might not exist inside the bubble. The specific masses and coupling constants that make carbon chemistry possible, that allow DNA and proteins and neural tissue, would be gone, replaced by whatever the new vacuum dictates. This bubble, once nucleated, would expand outward at the speed of light. The bubble wall, the boundary between the false vacuum and the true vacuum, moves at light speed. Nothing can travel faster than light. Any observer anywhere in the universe outside the bubble who sees the bubble wall approaching is seeing it arrive at the same speed as any signal that could have warned them. There is no warning. You cannot observe the bubble coming before it arrives, because nothing can outrun it. It arrives at the same moment as the light that shows it arriving. Physicists at Tsinghua University in Beijing published research in Physical Review Letters in 2026, describing a tabletop experiment using ultra-cold atoms arranged to simulate the dynamics of a quantum field in a false vacuum state. They observed bubble nucleation in real time, a key feature of false vacuum decay dynamics, and found that the decay rate increased with the strength of the symmetry-breaking field in ways consistent with quantum field theory's predictions. The experiment is an analog simulation, not a direct measurement of the Higgs field, but it tests the underlying physics of vacuum tunneling in a controlled setting for the first time. The lifetime of our universe's false vacuum, if it is indeed metastable, has been estimated at around 10 to the 790 years by some calculations, though this number is sensitive to precise values of the top quark mass and the Higgs mass and the calculation techniques used. 10 to the 790 years is astronomically larger than the roughly 10 to the 100 years of the black hole era. If this estimate is correct, the universe would reach heat death long before vacuum decay becomes probable. The heat death scenarios described in other sections remain the relevant framework. But different assumptions about the precise values of the measured parameters and different calculation methods can yield considerably shorter or longer estimates. The calculation is genuinely uncertain in ways that cannot be resolved without more precise measurements than current experiments provide. What is not uncertain is the physics of what happens when a false vacuum bubble arrives. If it does, it arrives without warning, at exactly the speed of light. Whatever it passes through is instantly converted to the new vacuum. Every atom, every particle, every quantum field transitions to the new configuration instantaneously. The person, the planet, the star, the galaxy it crosses, is not destroyed in any ordinary sense, not burned or crushed or exploded. It is rewritten. The physical laws that governed it change instantaneously, and whatever the new laws permit is what happens next inside the bubble. Given that the masses of elementary particles would change radically, atoms as we know them would not survive the transition. Chemistry would not survive. Biology would not survive. From outside the bubble, nothing would appear to change until the bubble wall arrived. From inside the bubble, the universe would look like itself for one final instant, and then be replaced by something alien. And the bubble keeps expanding, forever, at light speed, converting every region of space it touches from the false vacuum to the true vacuum, until, if it happens while the universe is still finite in extent, the entire cosmos has been rewritten. Part 8. Boltzmann Brains, the strange statistics of eternity. Assuming the Big Rip does not occur and false vacuum decay does not intervene, and the universe reaches the dark era after a Google years and continues from there, we encounter one of the most philosophically uncomfortable implications of modern cosmology. An implication that has forced cosmologists to revise theoretical frameworks they had considered settled. An implication that sits at the intersection of statistical mechanics, quantum field theory, and the philosophy of mind, and refuses to be categorized neatly as any of them. This is the problem of Boltzmann brains. The problem begins with a simple observation about the dark era. In the dark era, the universe is at thermal equilibrium, or very close to it, with a faint background temperature maintained by the quantum properties of its de Sitter expansion, something on the order of 10 to the negative 30 Kelvin. This temperature is extraordinarily close to zero, but it is not exactly zero, and a universe with any non-zero temperature, no matter how small, has thermal fluctuations. Random, statistical deviations from perfect equilibrium, in which local regions of space temporarily contain slightly more or less energy than the average. These fluctuations are inevitable. They are demanded by quantum statistical mechanics, in the same way that the random motion of molecules in a glass of water at room temperature is inevitable. The temperature of the water means the molecules are moving, and moving molecules fluctuate, and sometimes by pure chance, those fluctuations produce brief local arrangements of unusual order. In the dark era, the fluctuations are tiny and extraordinarily rare. The background temperature is so low, and the universe is so close to perfect equilibrium, that any meaningful departure from uniformity requires an enormous statistical improbability. But here is the key point. In infinite time, any event with non-zero probability must occur, not just once, infinitely many times. The probability of a fluctuation producing a given configuration does not reach exactly zero just because the configuration is very organized. It is merely very small. And in infinite time, very small probability, multiplied by infinite opportunities, produces infinite occurrences. What configurations can quantum and thermal fluctuations in the dark era produce, given infinite time? Small ones first, because small fluctuations are less improbable. A slightly energetic photon here, a temporary clustering of a few particles there, a brief local density enhancement that lasts for a moment and then disperses. These happen constantly, at the quantum level, in any finite temperature environment. But larger fluctuations are also possible, just vastly less probable. Given enough time, a fluctuation could assemble not just a few particles but many. Given much more time, a fluctuation could assemble a rock. Given much more time, a fluctuation could assemble a star. Given time so vast that the number of zeros required to write it out would fill a library, a fluctuation could, in principle, assemble a human brain. A complete, functional, self-aware human brain, assembled purely by statistical chance from the particles drifting in the dark era's void. This hypothetical entity, called a Boltzmann brain after the 19th century physicist Ludwig Boltzmann, who first entertained related ideas about statistical fluctuations, would be complete. It would have neurons. It would have synaptic connections in the patterns that produce memories and perceptions and sensations. It would, if it had a moment of consciousness before thermal noise disrupted it, experience itself as a mind embedded in a reality. It would believe it had a past. It would have apparent memories of a life, of experiences, of a world it inhabited. It would think, briefly, before the fragile statistical accident that created it dissolved back into the equilibrium from which it came. The timescale for a Boltzmann brain to form by spontaneous quantum fluctuation has been estimated at roughly 10 to the power of 10 to the 50 years, an incomprehensibly large number that requires 2 layers of exponentiation to write. But in a universe that lasts not just a Google years, but forever, this timescale is just a waiting time. Given eternity, not one Boltzmann brain would form, but infinitely many, each existing for a moment and then dissolving, scattered across the universe's endless future, like brief sparks in an infinite dark. This creates a problem that cosmologists take very seriously. It is called the Boltzmann brain problem, and it was first explicitly formulated as a problem for cosmology in the early 2000s by physicists including Andreas Albrecht and Lorenzo Sorbo, and subsequently explored by Sean Carroll, Don Page, and many others. The problem is this: if infinitely many Boltzmann brains form in the eternal dark era, and the total number of real, biologically evolved brains that ever existed during the stelliferous era is finite, then the vast majority of all minds that ever exist anywhere in the universe's history are Boltzmann brains. By a simple counting argument, any given observer is far more likely to be a Boltzmann brain than a real evolved brain. But Boltzmann brains have fundamentally unreliable memories and perceptions. They formed from random fluctuations. Their apparent memories are not records of actual past events, but statistical coincidences in the arrangement of matter that happen to resemble what memories look like. A Boltzmann brain that believes it is reading a page about cosmology, with apparent memories of learning physics and choosing to watch this video and sitting in a particular chair, cannot distinguish its fictitious memories from genuine records of experience. Its reasoning is not grounded in any reliable causal history. It is a brain that woke up, fully formed, believing it had a life, in the middle of an empty universe, and will dissolve back into nothing in moments. If you are more likely to be a Boltzmann brain than a real evolved brain, then you have no reliable basis for trusting any of your reasoning, including the reasoning that led you to this conclusion. A cosmological theory that predicts Boltzmann brain dominance is self-undermining. It destroys the epistemic foundation required to evaluate it. This is not merely a philosophical curiosity. It is a genuine constraint on cosmological models. Any model that predicts an infinite lifetime of de Sitter expansion, and thus an infinite number of Boltzmann brains, faces this problem head-on. Several responses have been proposed. Sean Carroll argues that the Boltzmann brain problem is a strong reason to believe that the de Sitter phase of the universe does not last forever, that the cosmological constant is not truly constant, but will eventually decay, transitioning the universe out of its dark energy-dominated phase before Boltzmann brains become numerically dominant. If the de Sitter vacuum decays after a finite time shorter than the Boltzmann brain formation timescale, the number of Boltzmann brains is controlled and the problem is mitigated. Other physicists argue that the Boltzmann brain problem reveals a fundamental tension in how we think about probability and observers in cosmology, and that resolving it requires a deeper understanding of the measure problem in eternal inflation and quantum cosmology, what it means to count observers in a universe that exists for infinite time. The Boltzmann brain problem is not resolved. It remains one of the places where cosmology, quantum mechanics, and the philosophy of mind intersect in a way that is genuinely uncomfortable and genuinely unresolved. Sitting with it honestly requires acknowledging that the question of what happens after the universe ends leads eventually, if you follow it far enough, to questions about what it means to be an observer, what it means to have reliable knowledge, and whether a universe that lasts forever is even internally consistent as a physical model. Part 9. Roger Penrose's Conformal Cyclic Cosmology, the Universe That Forgets. Of all the proposals for what comes after the universe ends, the one developed by the British mathematical physicist and Nobel laureate Roger Penrose is perhaps the most ambitious. Not because it proposes the most spectacular physics or the most exotic new particles, but because it suggests that the question itself is based on a wrong assumption. It suggests that the universe does not end in any final sense but cycles, aeon after aeon, through a process that makes the heat death of each aeon into the birth of the next. And it does this not by violating the second law of thermodynamics or by requiring new physics, but by a careful and mathematically precise argument about what the geometry of spacetime looks like at the two extremes, the very hot and dense beginning and the very cold and empty ending. Penrose shared the 2020 Nobel Prize in Physics for his mathematical proof that singularities form in the collapse of massive objects, work that was foundational to the modern theory of black holes. He has been developing conformal cyclic cosmology, or CCC, since the mid-2000s, and it represents his attempt to resolve one of the deepest problems in modern cosmology. Why was the Big Bang low entropy? The problem runs as follows. The second law of thermodynamics tells us that entropy always increases. The universe began 13.8 billion years ago in a state of low entropy, an extraordinarily smooth, ordered initial condition that allowed all the subsequent structure, stars, galaxies, planets, life, to form as the universe evolved toward higher entropy states. This is exactly what we observe. The universe has been doing what low entropy systems do, organizing complexity as it moves toward equilibrium. But here is the puzzle. If you take the equations of physics and run them in reverse, asking what initial condition would be needed to produce a universe like ours, the answer is a very specific, very smooth, very special configuration. If you take the equations of physics and ask what fraction of all possible initial configurations would produce a universe like ours, the answer is an extraordinarily small fraction. The physicist Roger Penrose himself calculated, using a counting argument based on the size of the Weyl curvature tensor at the Big Bang, that the probability of the initial conditions of our universe occurring by chance is roughly 1 in 10 to the 10 to the 123rd power, a number so incomprehensibly small that writing it out would require a piece of paper larger than the observable universe. Standard inflationary cosmology addresses this problem partially by proposing that a brief period of exponential expansion in the first tiny fraction of a second after the Big Bang smoothed out any inhomogeneities and made the initial conditions look flat and uniform regardless of what they were before inflation. But Penrose argues that inflation does not fully solve the low entropy problem. It explains the spatial flatness and large-scale uniformity of the universe, but it does not explain why the Weyl curvature, the component of spacetime curvature associated with gravitational waves and tidal distortions, was so precisely zero at the Big Bang. The Weyl curvature hypothesis, which Penrose himself proposed, states that the initial singularity of the Big Bang had vanishing Weyl curvature. This is an extremely special condition, and inflation does not explain why it held. Penrose's CCC proposes that this condition is not special at all. It is the natural outcome of the previous eon's heat death. The argument goes like this. When all the black holes in the universe have evaporated through Hawking radiation, and when all massive particles have either decayed or been absorbed by those black holes before their evaporation, the universe is left with only massless particles. Photons, hypothetical gravitons, potentially massless neutrinos if they turn out to be massless. And massless particles have a remarkable mathematical property. They do not experience time in the ordinary sense. For a photon, the proper time along its world line, the time measured by a clock moving with the photon, is always zero. This is a consequence of special relativity. Massless particles always travel at the speed of light, and at the speed of light, time does not pass from the particle's own perspective. This means that a universe populated only by massless particles, like the late dark era before any fluctuations have assembled more complex structures, is a universe in which the physical concept of time becomes degenerate. Distances are still meaningful. Directions are still meaningful. Angles are still meaningful, but the absolute scale of distances loses physical significance because there are no massive particles to serve as rulers. Massive particles have a natural length scale, their Compton wavelength, related to their mass through quantum mechanics. Without massive particles, there are no natural length scales, and the physics of the universe becomes invariant under rescaling of all distances by any factor. This mathematical property is called conformal invariance, and a geometry that preserves angles but not distances is called a conformal geometry. The key insight of CCC is that both the very end of an aeon, a conformally invariant universe of massless particles expanding toward infinity, and the very beginning of an aeon, the initial singularity of a Big Bang which also has zero Weyl curvature and a specific conformal structure, are both smooth conformal boundaries. One is an infinite future boundary, the other is an infinitely compressed past boundary. But in conformal geometry, where absolute scale does not matter, these two boundaries can be matched to each other. Penrose proposes that nature actually performs this identification. The infinitely expanded future of one eon, conformally rescaled by the loss of all massive particles and all length scales, becomes the compact initial singularity of the next eon. The transition requires no collapse, no big crunch, no reversal of the expansion. The universe simply keeps expanding, and at the conformal boundary, the mathematical equivalence between infinity and zero allows one aeon's end to become the next aeon's beginning. The low entropy of each aeon's Big Bang is explained not by any special fine-tuning, but by the smooth, whale curvature zero conformal structure that the previous aeon naturally produces when all its massive particles have been eliminated and only massless radiation remains. The key mechanism that makes this work, from a thermodynamic perspective, is black hole evaporation. Black holes are the universe's entropy reservoirs, objects with extraordinarily high entropy relative to their size. The Bekenstein-Hawking entropy of a black hole is proportional to its event horizon area, not its volume, a feature that makes black holes the most efficient possible entropy storage devices. When all black holes in the universe evaporate through Hawking radiation, that stored entropy is released as thermal radiation. Photons with no information content about the specific configurations that fell into the black holes. The universe after black hole evaporation is at high entropy, yes, but its entropy is stored in a highly diluted, featureless, conformally smooth radiation field, which is exactly the type of conformally invariant state that can be matched to a new low-entropy Big Bang through the conformal rescaling. Penrose's CCC makes specific predictions that are, in principle, testable. The collisions and mergers of supermassive black holes during the final stages of the previous eon's black hole era would have emitted powerful gravitational waves. These waves would have propagated through the conformal transition and appeared in the cosmic microwave background of our aeon as faint, concentric, ring-shaped patterns of slightly different temperature. These rings, which Penrose calls Hawking points in honor of their origin in the Hawking radiation of previous aeon black holes, are a specific prediction of CCC that distinguishes it from the standard inflationary cosmology. Penrose and his collaborators, including astronomer Vahe Gurzadian, have published multiple analyses claiming to find evidence of these concentric rings in the WMAP and Planck CMB data. The claims are contested. Several independent groups have analyzed the same data and concluded that the apparent rings are consistent with statistical noise and do not constitute a significant detection. The debate has been ongoing for more than a decade and has not been resolved. Most cosmologists remain skeptical of the claimed detection, though they do not dispute the theoretical framework's mathematical elegance. What is beyond dispute is that CCC is a serious, mathematically rigorous proposal developed by one of the leading mathematical physicists of the past century, and it offers a genuinely novel answer to the question of what comes after the universe ends. The answer is another universe, built from the mathematical ashes of this one, inheriting no memories, no structures, no histories, carrying forward only the conformal geometry that our eon's final state provides as a smooth initial boundary. Our universe's heat death is another universe's Big Bang. The ending is the beginning. Part 10. After the end, what physics cannot yet tell us, and what it can. We have followed the universe from the death of the last red dwarf through the dissolution of matter, through the long darkness of the black hole era and the evaporation of the last supermassive black hole, through the silence of the dark era and the strange implications of infinite time, through the possibility of violent ends and quantum endings and mathematical rebirths. And throughout all of it, we have been honest about what is known and what remains genuinely open. Let us take stock. The timeline of the universe through the stelliferous era is as well grounded in observational physics as cosmology gets. The stellar lifetimes of red dwarfs, the formation of white dwarfs and neutron stars, the cooling of stellar remnants, the eventual exhaustion of star-forming gas. All of this follows from stellar physics that has been tested and refined over a century of observation. We know, with high confidence, that the stelliferous era ends, that star formation ceases, that the night sky of the far future goes dark. We do not know exactly when the last red dwarf will go cold, because we do not know the full mass distribution of all stars in all galaxies. But we know it happens within the range of 1 to 100 trillion years from now. The degenerate era's broad timeline follows from well-established quantum mechanics. Electron degeneracy pressure is a measured physical phenomenon. White dwarfs are observed objects and their cooling rates match theoretical predictions. The key uncertainty is proton decay, which has been theoretically motivated by grand unified theories for 50 years, but has never been directly observed. If protons decay on the predicted timescales, the degenerate era ends with ordinary matter dissolved. If they do not, other quantum processes dismantle matter on longer timescales. Either way, ordinary matter is finite. Hawking radiation and black hole evaporation are theoretically well established, resting on a convergence of quantum mechanics and general relativity that is among the most celebrated calculations in modern physics. The calculation has been verified by multiple independent methods and is considered correct by virtually all working theorists, even though the radiation itself has never been directly observed from astrophysical black holes, because the Hawking temperature of any black hole we could detect is far too cold to measure against the background radiation. The broad outlines of the black hole era follow from Hawking's result. Beyond the dark era, the picture becomes less certain. Whether dark energy is a true cosmological constant or phantom energy, a question whose answer determines whether the universe ends in heat death or the Big Rip, is currently an open observational question. Whether the Higgs field is metastable, a question that determines whether false vacuum decay is a threat, is currently an open theoretical question whose answer depends on precise measurements of particle masses that are at the edge of current experimental capability. Whether conformal cyclic cosmology is correct is a question that is theoretically interesting and experimentally contested. Whether the Boltzmann brain problem represents a real constraint on cosmological models or a confusion about how to count observers in infinite time scenarios is a philosophical and theoretical question that has not been resolved. And deeper than all of these specific questions is a more fundamental one. When we ask what happens after the universe ends, we are asking what the laws of physics say about conditions beyond the domain where those laws have been tested. The laws of physics we know describe the evolution of systems within spacetime, from some initial condition to some later condition. They do not address what initial conditions are preferred, why there is something rather than nothing, or what happens at the boundaries of spacetime itself, the Big Bang singularity, and the conformal boundary of an infinitely expanded future. These boundary conditions are outside the scope of the known laws. They are inputs, not outputs, of the theories. Quantum gravity, the long-sought unification of quantum mechanics and general relativity, might change this. It might provide a framework in which the initial conditions of the universe are determined by the theory itself, rather than being fed in by hand. The Hartle-Hawking no-boundary proposal, which suggests that the universe has no temporal boundary because time becomes imaginary near the Big Bang singularity in quantum gravitational terms, attempts to do exactly this. Loop quantum gravity, with its suggestion that spacetime is made of discrete quantum spin networks at the Planck scale, might provide a language for discussing what happens at the endpoints of spacetime. String theory, with its landscape of possible vacuum states and the idea that our universe is one bubble in an eternal inflationary multiverse, provides a different context entirely for asking what comes before or after any given aeon. None of these frameworks is complete. None has made unambiguous, confirmed predictions at scales accessible to current experiments. The gap between the theoretically motivated ideas and the experimentally confirmable predictions is the central challenge of contemporary fundamental physics. But here is what strikes me. Sitting in the middle of the stelliferous era, in the warm and temporary light of a star that has been burning for 4.6 billion years and will burn for another 5 billion, on a planet covered in liquid water and living organisms and atmosphere, the question itself is extraordinary. The fact that matter, organized into nervous systems through 4 billion years of evolution, can contemplate the timescale of the black hole era, can calculate the Hawking temperature of a supermassive black hole, can formalize the conformal geometry of the boundary between two cosmic eons, can worry seriously about Boltzmann brains, is not something the laws of physics require. There is nothing in the equations of quantum field theory or general relativity that demands the emergence of self-aware systems capable of doing cosmology. It is a contingent fact about our specific universe, about the specific values of its physical constants, about the specific initial conditions that allowed stars and planets and chemistry and biology to arise during this particular stelliferous era. We are, in the most literal sense, a brief arrangement of atoms in a temporary cosmos, looking out at a universe that has been going on for billions of years before we arrived, and will continue for trillions and then incomprehensibly longer periods after we are gone. The question of what happens after the universe ends is not a question we are obligated to care about. Nothing in our evolutionary history required us to think on these timescales. Nothing in the day-to-day task of survival or reproduction or social cooperation demands any concern with the fate of the last black hole. And yet here we are, caring anyway, thinking about it anyway, following the argument wherever it leads, past the comfortable familiar timescales of human history and geological time, and even stellar evolution, out into the desolate reaches of cosmological decades 40 and 60 and 100, out into the infinite silence of the dark era, out past the last Hawking flash, into the question of what, if anything, comes next. Doing this not because we have to, but because the universe, through us, seems to be one of the ways it has discovered how to think about itself. That is either a profound observation or a grandiose one, depending on your temperament. What is not in dispute is the scale of what we have been thinking about. The universe has been doing extraordinary things for 13.8 billion years. It will continue doing extraordinary things, or extraordinary versions of nothing, for intervals so large that our current age is a rounding error. We sit in the middle of the brightest era this universe will ever have, a brief warm interval between two incomprehensible darknesses, surrounded by the light of 200 billion stars in our galaxy alone, and if we look carefully, in every direction, the sky is full of the light of 1 trillion galaxies, each containing hundreds of billions of stars, all of it temporary, all of it burning on borrowed time, all of it heading, slowly and inevitably, toward the cold and dark. Every white dwarf cooling in the darkness of a future galaxy carries the memory of a star's billion-year life within its carbon and oxygen lattice, radiating away the last of it at a rate so slow it will take longer than the current age of the universe just to cool a fraction of a degree. Every black hole drifting through the black hole era, dark and patient and impossibly dense, carries within its event horizon the information content of everything that ever fell into it, in a form that may or may not be recoverable, but that the laws of physics insist was not destroyed. And somewhere, perhaps, across a conformal boundary that our equations describe but our intuitions cannot fully reach, the quiet, massless radiation of a dying eon is being prepared, by the mathematics of conformal geometry, to become the hot, dense birth of a new one. The light goes out. The dark is very, very long. And then, if Penrose is right, or if something even stranger is right that we have not yet found, the light comes on again. Every time. If the universe's long story is what brought you here, you are in exactly the right place. Drop a comment below, genuinely anything, where you are, what time it is, what surprised you, what you want to think about next. And if you are not subscribed yet, this is the video that probably means you should be. Thanks for making it all the way to the end. Additional depth, the physics of the very long run. There are several threads in the story of the universe's end that deserve more careful examination than the broad narrative above allows. The science is genuinely complex, and the details are where the real strangeness lives. So let us go deeper on a few of the most important aspects. The Sun's actual death and what it means for Earth. The death of the stelliferous era is a timeline measured in trillions of years, but the death of our own star, the Sun, is a much more personal and much more near-term event, though near-term here still means billions of years. Understanding what happens to the Sun tells us exactly what is coming for the rest of the cosmos's ordinary stars, in a kind of preview. Right now, the Sun is a middle-aged main sequence star. It converts roughly 620 million tons of hydrogen into helium every second. This sounds prodigious, but the Sun contains approximately 1.9 times 10 to the 30th kilograms of material, of which roughly 70% is hydrogen. It has been fusing hydrogen for about 4.6 billion years, and it has consumed roughly half its core hydrogen in that time, leaving another 5 billion years of main sequence burning ahead of it at roughly current rates. As the Sun ages and its core becomes increasingly depleted of hydrogen, the core contracts slightly under gravity, raising its temperature, which causes the hydrogen-burning shell outside the core to intensify. The increased energy output causes the Sun's outer layers to expand enormously. In roughly 5 billion years, the Sun will swell into a red giant, its outer atmosphere expanding to roughly 200 times its current radius, enough to reach the current orbit of the Earth. The Earth, by this point, will have been sterilized of all life long before the red giant phase, as the gradually increasing solar luminosity over the intervening billions of years raises surface temperatures beyond what liquid water can sustain. Life on Earth ends in the heat of a brightening sun, not the cold of a dead one. But that is a 1 to 1.5 billion year timescale, depending on how you define habitability. After the red giant phase, the Sun will eject roughly half its mass in a planetary nebula, a shell of ionized gas expanding into space. The remaining core will contract into a white dwarf, roughly the size of the Earth but containing about half the Sun's original mass. The white dwarf will begin to cool immediately. After roughly 1 billion years, it will have cooled to around 6,000 Kelvin, dimmer than the Sun is now, but still detectable as a faint white star. After 10 billion years, it will have cooled to around 4,000 to 5,000 Kelvin, the color of an orange star. After 100 billion years, it will be around 3,000 Kelvin, just barely above what we might call a warmly glowing coal. After a trillion years, it will have cooled below 1,000 Kelvin. After roughly 10 trillion years, it approaches what we would consider the background temperature of the universe. By this point, it is functionally a black dwarf, a cold, dark, inert sphere of carbon and oxygen, drifting forever through space. The planetary nebula it expelled will have long since dispersed into the interstellar medium, its hydrogen and helium recycled eventually into the next generation of stars. The heavy elements forged in the Sun's core and in any pre-solar stars that contributed to the solar nebula when it formed will persist, carried forward as trace elements in the interstellar medium, available to be incorporated into future stars and perhaps future planetary systems. The Sun's matter does not disappear. It is redistributed, transformed from one structural form into another, carried forward through the cosmos in new configurations. This is the fate of every Sun-like star in the universe. Every G-type main sequence star within a few hundred light-years of the Earth is going through essentially the same story on a similar timescale, give or take a few billion years. Every star more massive than the Sun is going through a faster version of the same story, spending less time on the main sequence and ending either as a white dwarf, a neutron star, or a black hole depending on its mass. Every star less massive than the Sun is going through a slower version, spending more time as a red dwarf and then cooling to a black dwarf over trillions rather than billions of years. The whole gallery of stellar fates, supergiants that explode in core collapse supernovae and leave behind neutron stars or black holes, intermediate mass stars like the Sun that form planetary nebulae and white dwarfs, low-mass red dwarfs that cool slowly to black dwarfs, is the universe exhausting the structural possibilities it created in the first few 100 million years after the Big Bang, when the first stars began to form. All of those possibilities are temporary. All of those configurations are borrowed time. The cosmic web and its fate. The large-scale structure of the universe, the vast network of filaments and walls and voids that organizes galaxies and galaxy clusters into a web-like pattern visible on scales of hundreds of millions of light-years, is itself a transient structure. It formed over the first few billion years of cosmic history as dark matter and ordinary matter gravitationally collapsed along the density fluctuations seeded by quantum variations in the inflationary epoch, and it has been growing in contrast and definition ever since, as gravity continued to amplify those initial overdensities. Within the cosmic web, galaxies are strung along filaments like beads on a string. Galaxy clusters sit at the intersections of filaments, where the greatest concentrations of matter have accumulated. Giant voids, regions nearly empty of galaxies, occupy the spaces between. The universe we see when we look out with large galaxy surveys is this structure, this web, the large-scale architecture of matter, organized by 13.8 billion years of gravitational work. As the universe continues to expand and dark energy continues to dominate, the cosmic web stops growing. The density fluctuations that seeded it have already collapsed into the structures we see, and there is not enough remaining matter in diffuse form to continue building new large-scale structure. The filaments and walls reach an asymptotic configuration and then begin to dissolve as dark energy's expansion carries their constituent galaxies apart. Within each gravitationally bound cluster or group, the matter remains together. But between clusters, the filaments that connect them stretch and thin as the universe expands. Galaxies that are marginally bound to filaments may be stripped away by expansion. The web does not hold together forever. On timescales of a few trillion years, the large-scale structure of the universe that is so beautifully apparent in current galaxy surveys will have largely erased itself. Each gravitationally bound cluster will have consolidated into a single merged galaxy or small group of galaxies. The filaments between them will be empty. The voids will have grown. The universe will look not like a web, but like a collection of isolated island galaxies separated by enormous, empty expanses of space. It will have simplified. It will have lost the hierarchical structure it spent billions of years building. The fate of dark matter. Throughout the stelliferous era and into the degenerate era, dark matter remains a significant part of the universe's energy budget. Dark matter, which makes up roughly 27% of the total energy density of the universe compared to ordinary matter's roughly 5%, has been the gravitational scaffolding on which ordinary matter built all its structures. The dark matter halos surrounding galaxies, which Vera Rubin's flat rotation curve measurements first pointed toward, and which have been confirmed by a century of subsequent observations, hold galaxies together and provided the initial density perturbations around which galaxies formed. But what is dark matter? As of 2026, this remains one of the most pressing open questions in physics. Dozens of candidate particles have been proposed, from weakly interacting massive particles, to axions, to sterile neutrinos, to primordial black holes. The most popular theoretical candidate through much of the 2000s and 2010s was the WIMP, or weakly interacting massive particle, a class of particles predicted by supersymmetric extensions of the standard model of particle physics. Decades of direct detection experiments that used ultra-sensitive detectors buried deep underground to look for the rare interaction of a dark matter particle with an atomic nucleus, have found no confirmed dark matter signal. If WIMPs exist, they interact with ordinary matter far more weakly than the most optimistic theoretical predictions suggested. Whatever dark matter is, its fate in the long-term future of the universe depends on its properties. If dark matter particles are stable and non-interacting, they may persist indefinitely in the dark era as a diffuse, non-interacting component of the universe's final state, alongside the photons and leptons. If dark matter particles decay on some timescale, their decay products would have been radiated away during the degenerate era. If some dark matter is in the form of primordial black holes, those black holes would evaporate through Hawking radiation during the black hole era like any other black hole, depending on their mass. The fate of dark matter is tied to its unknown identity, the information paradox, and what it means for memory. One of the most important unresolved problems in fundamental physics, one that connects directly to the question of what happens after the universe ends, is the black hole information paradox. When an object falls into a black hole, all of its specific properties, its composition, temperature, structure, the particular arrangement of its matter, seem to be lost behind the event horizon. The black hole retains only the total mass, the total charge, and the total angular momentum of everything that fell into it. This is sometimes called the no-hair theorem. Black holes have no hair, meaning no specific distinguishing features beyond these three quantities. When the black hole later evaporates through Hawking radiation, it radiates purely thermal radiation, radiation with a temperature determined solely by the black hole's mass. Thermal radiation carries no specific information about the particular configuration of matter that fell in. If a library of books falls into a black hole and the black hole evaporates, where does the information in those books go? Hawking's original 1974 calculation suggested it was simply destroyed. This would violate a fundamental principle of quantum mechanics, which states that quantum information is never destroyed, only transformed and redistributed, a principle called unitarity. The tension between general relativity's prediction that information disappears behind event horizons and quantum mechanics' insistence that information is always conserved is the information paradox. It has been one of the central problems in theoretical physics for 50 years. Progress was made in 2019 and 2020 when multiple groups of physicists, using techniques from quantum gravity and holography, calculated what is called the Page curve, a theoretical prediction for how the entropy of Hawking radiation from a black hole should evolve over the full course of its evaporation if quantum mechanics is respected. Earlier work by Don Page in 1993 had predicted that if information is conserved, the entropy of the Hawking radiation should first increase as the black hole evaporates, peak at roughly half the black hole's lifetime, and then decrease as the remaining radiation becomes increasingly correlated with the earlier radiation, encoding the information about what fell in. The recent calculations confirm that this behavior follows from quantum gravitational effects near the end of a black hole's life, suggesting that information is indeed recovered and Hawking's original result was incomplete. If information is truly conserved through black hole evaporation, then the Hawking radiation emitted by every black hole throughout the black hole era contains, in the subtle quantum correlations between individual photons and particles, the complete information content of everything that ever fell into those black holes. The history of every galaxy, every star, every civilization that ever fell past a galactic center, every proton that was swallowed in the billions of years of accretion, is encoded in the thermal radiation that fills the dark era. Not in any accessible form, not in any form that could be reconstructed in practice with any technology, but present in principle, in the sense that the quantum state of the universe in the dark era contains the history of the universe in the stelliferous era. The dark era is not a state of amnesia, it is a state of perfect but thoroughly scrambled memory. The universe knows everything that happened in it. It just has no way to tell anyone. The arrow of time and its dissolution. The experience of time as a one-way flow from past to future is so fundamental to human consciousness that it is easy to mistake it for a feature of the laws of physics rather than a feature of our particular position in the universe's history. But the fundamental laws of physics, the equations of quantum mechanics and general relativity and quantum field theory, are largely time-symmetric. They work equally well in both temporal directions. A video of fundamental particle interactions played backward is physically valid. The asymmetry of time, the irreversibility of experience, the sense that the past is fixed and the future is open, is not written into the microscopic laws. It emerges from the macroscopic statistical behavior of large numbers of particles moving from lower to higher entropy states. The arrow of time exists because we live in a universe that began in an extraordinarily low entropy state and has been increasing in entropy ever since. The direction of time is the direction of increasing entropy. Eggs break, but do not reassemble spontaneously. Ice melts in warm rooms, but does not spontaneously form. Stars burn out and do not spontaneously ignite from a dark, diffuse state. All of these irreversible processes happen because they increase entropy, because they move from less probable to more probable configurations. The statistical asymmetry between the extraordinarily improbable past state and the much more probable future states is what gives time its direction. In the dark era, entropy is maximized. Every configuration is equally probable. There is no thermodynamic distinction between one moment and another. The arrow of time does not simply slow down in the dark era, it disappears. Time still exists as a coordinate in the equations, but the physical content of that coordinate is empty. The universe in the dark era does not have a thermodynamic past and a thermodynamic future. It has only an undifferentiated eternal present, broken occasionally by quantum fluctuations that have no directional significance. Some philosophers of physics argue that this means the dark era is in a real sense timeless, that the universe in the dark era has no more temporal structure than a sphere has a top and bottom. Time only has meaning when there are processes, and processes require entropy gradients, and entropy gradients require a special past. When the past becomes indistinguishable from the future, time as we experience it ceases. This is a genuinely profound implication. It means that the deepest question about what happens after the universe ends is not a question about events or physics. It is a question about whether there is a meaningful sense of after when there is no thermodynamic arrow to give the word content. The universe does not end because it runs out of time. It ends because time, as a concept with physical meaning, exhausts itself. The clocks stop not because they break, but because the concept of before and after that they were measuring dissolves into a symmetric eternal equilibrium. Unless, of course, something breaks the symmetry again. Unless a quantum fluctuation large enough to create a new low-entropy region manages to occur, or a conformal boundary allows a new aeon to begin, or a false vacuum bubble creates a region with new physics that starts the whole process over. In any of those cases, the arrow of time would re-emerge from the dark era's eternal symmetry, pointing confidently in the direction of increasing entropy in the new system, as if it had never been interrupted. The rarity of this moment. It is worth pausing, before the end, to say something about where we are in the story. We are currently at approximately cosmological decade 10. The stelliferous era spans from cosmological decade 6 to cosmological decade 14. We are in the middle of the brightest era the universe has ever had or will ever have. The black hole era alone, spanning from cosmological decade 38 to cosmological decade 100, represents more time than will have elapsed from the Big Bang to the present day, multiplied by 10 to the 90th power. The degenerate era adds more on top of that. The dark era, strictly speaking, never ends. Against this backdrop, the 13.8 billion years of the universe's history, everything from the Big Bang through the formation of the first galaxies and the first stars and the gradual building of cosmic structure and the 4.6 billion years of our solar system and the 4 billion years of life on Earth and the roughly 300,000 years of anatomically modern humans and the roughly 12,000 years of agricultural civilization and the 400 years since Galileo first pointed a telescope at the sky, constitutes an event so brief relative to the universe's expected future that it is, in a very precise sense, essentially instantaneous. We are living in the opening nanosecond of a very long story. The conditions that allow us to exist, that allow carbon chemistry and liquid water and biology and cognition, are conditions that apply specifically to this brief bright era. Stars are required. Not just any stars, but stars like the sun, large enough and hot enough to generate the heavy elements, small enough and long-lived enough to allow planetary systems the billions of years needed for life to evolve. The stellar era lasts perhaps 100 trillion years. The universe's total expected lifetime, if the dark era truly lasts forever, is infinite. We live in the first 100 trillionth of the universe's total span of time, during the only window in which the universe is bright enough and chemically rich enough to support what we would recognize as life. This is not a reason for gloom. It is a reason for something closer to wonder. We are here during the golden interval, the brief warm window between the darkness of the pre-stellar universe and the darkness of the post-stellar universe, and we have developed the cognitive tools to look both directions and understand what we see. We can look backward with telescopes and particle physics and nuclear chemistry and read the record of the first microseconds after the Big Bang. We can look forward with theoretical physics and mathematics and project the story of the cosmos forward to timescales that make the age of the universe look like a heartbeat. We do this from inside the story, in the middle of the brief, bright chapter, using the same physical processes that make the story possible. Neurons made of carbon and oxygen and phosphorus, all forged in the cores of stars that lived and died before the sun was born, organized by 4 billion years of biological evolution on a rocky world in the habitable zone of an ordinary star, thinking about the end of the universe that made them. There is something in that which resists being described as meaningless, even if you are committed to finding no meaning in the cosmos. The universe produced something capable of understanding itself, briefly, during the only window in which understanding of this kind was possible. Whether that is significant in any deep metaphysical sense is a question beyond the reach of physics, but it is, at minimum, a remarkable fact. The final inventory. Let us end with an honest accounting. What do we know? What remains genuinely open? We know, with high confidence grounded in observational evidence and well-tested physical theory, that star formation will eventually cease, that stars have finite lifetimes, that white dwarfs, neutron stars, and black holes are the end products of stellar evolution, that black holes emit Hawking radiation, that the universe is currently in an accelerating expansion driven by dark energy, that the stelliferous era is finite, that matter's long-term fate depends on whether protons decay, that the black hole era, if it occurs, lasts on timescales measured in Google years, that the dark era is characterized by maximum entropy and fading thermodynamic meaning. We know, as theoretical frameworks with varying degrees of empirical support, that the Big Rip is possible if dark energy is phantom energy, which current data neither confirms nor rules out, that false vacuum decay is possible if the Higgs field is metastable, which current particle physics measurements suggest is plausible but uncertain, that conformal cyclic cosmology is an internally consistent mathematical framework whose observational predictions are contested, that Boltzmann brains are a genuine theoretical problem for any cosmological model that predicts infinite de Sitter expansion. We do not know, and cannot currently determine from existing theory or experiment, the exact nature of dark energy, and whether it is constant, whether protons decay, the exact lifetime of the false vacuum if it is metastable, whether information is genuinely recovered from Hawking radiation or is destroyed, whether quantum gravity modifies the behavior of spacetime at the conformal boundaries CCC proposes, what, if anything, preceded the Big Bang, whether the universe is genuinely infinite in extent or finite, and whether the question of what happens after the universe ends has an answer within physics as currently formulated, or requires a fundamentally different theoretical framework. Those open questions are not a failure. They are the frontier. They are the places where the story is still being written, where mathematics and observation are still probing the edges of what can be known. The history of physics is a history of expanding the circle of what can be understood, and there is no reason to believe that circle has reached its final extent. What is not open, what is as certain as anything in science, the universe we live in is temporary. The light is borrowed. The order is finite. The entropy is increasing. And somewhere down the long corridor of time, past all the eras we have described and perhaps past things we have not yet imagined, the question of what comes after will still be the right question to ask, even if no one is left to ask it. The universe has been telling this story since before time had anyone to measure it. We caught it in the middle. We have about 5 billion years left before our star exhausts itself, and perhaps a trillion years before the last red dwarf in our galaxy goes dark. In the context of the universe's biography, that is still the opening chapter. The pages ahead are mostly blank. And the most honest thing physics can say about those blank pages is this: we have the equations, we have some of the answers, and the ones we do not have yet are the most interesting ones. Keep looking up. The universe rewards attention, even at this scale. The deep quiet and the numbers we cannot speak. There is a particular kind of vertigo that comes from working with the numbers in this subject, and it is worth addressing directly rather than glossing over it with generalities. When we say the black hole era lasts a Google years, or that the Boltzmann brain formation timescale is 10 to the power of 10 to the 50 years, we are not just using big numbers for rhetorical effect. These numbers have a specific meaning, and that meaning is genuinely strange. A googol, 10 to the 100, is a number so large that if you tried to write it out in standard notation, you would need 100 digits. The number of atoms in the observable universe is roughly 10 to the 80. A googol is 10 billion times larger than the number of atoms in the observable universe. If every atom in the observable universe were itself an observable universe, the total number of atoms in all of those nested universes would still be smaller than a googol. This is the timescale of the black hole era's end, a googol years. Now consider the number 10 to the power of 10 to the 50. To write this out, you would first need to write 10 to the 50 zeros. That is a number with 100 quadrillion zeros in it. A book containing that many zeros would have to contain 100 quadrillion pages. If each page were a millimeter thick, the stack of pages would extend for a distance of 100 trillion kilometers, which is roughly 10 light years, farther than the nearest star. The number 10 to the 10 to the 50 is larger than 10 to the 100 by so many orders of magnitude that expressing the ratio requires its own incomprehensible numbers. This is roughly the timescale for a Boltzmann brain to form from quantum fluctuations. And yet, in an infinite universe, these numbers are just waiting times. They are large but not infinite. In infinite time, not just a Boltzmann brain but a Boltzmann galaxy, a Boltzmann version of the entire observable universe, assembles from quantum fluctuations. Every possible configuration of matter and energy that is consistent with the laws of physics will eventually be assembled by random fluctuations in an infinite heat-death universe, including, almost certainly, a perfect copy of the state of the universe right now, complete with every galaxy, every star, every planet, every person, every memory, every thought being thought at this moment, assembled not from a Big Bang, but from a statistical fluctuation in an empty void, including a copy of this video watched by a copy of you who has no reason to suspect that they are a Boltzmann configuration rather than the product of 13.8 billion years of genuine cosmic evolution. This is why the Boltzmann brain problem is not considered merely philosophical by working cosmologists. It undermines the self-consistency of theories that predict infinite de Sitter expansion, because in such theories the vast majority of observers are Boltzmann configurations, and Boltzmann configurations cannot trust their own reasoning or observations. Any cosmological theory that predicts you are probably a Boltzmann brain is a theory that predicts you are probably wrong about the theory, a self-undermining loop. The resolution almost certainly involves understanding that the de Sitter phase of the universe does not in fact last forever. Something happens to terminate it. Perhaps the cosmological constant decays. Perhaps quantum gravity effects become relevant near the conformal boundary and change the physics. Perhaps the conformal cyclic cosmology transition occurs. Whatever terminates the de Sitter phase also limits the production of Boltzmann brains and restores the self-consistency of cosmological reasoning. But we do not know what terminates it, or even with certainty that it is terminated. We are working at the edge of what our current theories can reliably say. The stars we can no longer see. There is an observational consequence of dark energy's expansion that is already happening, right now, that is worth sitting with as a concrete reminder of the universe's temporal structure. The expansion of the universe carries distant galaxies away from us. Beyond a certain distance, called the Hubble radius, galaxies are receding from us faster than light, not because anything is moving faster than light through space, but because the space between us and those galaxies is expanding faster than light can traverse it. Light emitted by those galaxies will never reach us. The Hubble radius is currently about 14 billion light-years. Galaxies farther than this are already effectively beyond our reach, even though we can sometimes see them because light they emitted long ago, when they were closer, is still traveling toward us. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is larger, about 46 billion light-years in radius, because of the way expansion affects light's travel. As the universe continues to expand, the Hubble radius stays roughly constant, or grows slowly, while the distance to individual galaxies grows faster. Galaxies that are currently within our observable universe, which we can detect with our telescopes, will eventually cross the cosmological horizon, and their light will no longer be able to reach us. This process is already happening. The galaxies we can currently observe with the James Webb Space Telescope, some of them more than 13 billion light-years away, are moving away from us. The photons they are emitting right now will take longer and longer to reach us, redshifted to longer and longer wavelengths by the expansion, and eventually the stream of photons arriving from those galaxies will thin to nothing. In roughly 2 trillion years, the last photons from the most distant currently observable galaxies will have arrived, and no further photons will follow them. Those galaxies will not cease to exist. They will simply have moved beyond the horizon of what we can ever observe. The night sky will be empty beyond our local group, not because the universe is empty beyond the local group, but because the expansion has put everything else permanently beyond reach. An astronomer, in 2 trillion years, would look out at the sky and see Milkomeda, the merged result of the Milky Way, and whatever of the local group has merged into it by then, and nothing else. No galaxy surveys, no quasar catalogs, no CMB maps showing the temperature fluctuations that encode the density perturbations of the early universe. All of that evidence for the Big Bang will have redshifted to energies too low to detect. The universe will look, to that hypothetical astronomer, like it has always been just this one galaxy, isolated in a sea of dark. The evidence that the universe had a beginning, that there was a Big Bang 2 trillion years before their moment, will be lost to the expansion. Stephen Hawking and his collaborators wrote about this in the context of what they called the loss of information from the observable universe. Not just individual particles falling into black holes, but entire histories, entire branches of cosmic evolution, falling permanently beyond horizons. The universe, as it expands, loses the ability to observe its own past. The Big Bang becomes unobservable, not because the evidence was never there, but because expansion carried it away. And 2 trillion years from now, the last astronomer looking at an empty sky will have no way to know that the universe they are in began in a hot, dense state 2 trillion years earlier, surrounded by 1 trillion galaxies, alive with the light of stars. They will be, in a very specific observational sense, wrong about the universe they inhabit, not because they are foolish, but because the evidence has been removed from their light cone. This is not a uniquely future problem. There are things about our own universe that are already beyond our observational horizon, events from before the epoch of last scattering, the moment 380,000 years after the Big Bang when the universe became transparent and released the cosmic microwave background, that we cannot access by any direct observation. The boundary of what any observer can observe is always finite, always limited by the speed of light and the history of expansion, always smaller than the full extent of what exists and has existed. Life in the degenerate era. This is speculative, clearly labeled as such, but it is the kind of speculation that serious physicists have genuinely entertained. Adams and Laughlin, in their book The 5 Ages of the Universe, asked not just what the universe would look like in the degenerate era, but whether any form of life or intelligence could persist into it. It is a question worth exploring, if only to understand how different future conditions are from current ones. During the stelliferous era, life as we know it depends on a continuous supply of energy from a difference in temperature. The sun is hot, space is cold. The gradient drives everything on Earth, photosynthesis, which captures solar photons and stores their energy in chemical bonds, the weather and ocean circulation systems that distribute that energy, the metabolic processes of every living thing on the planet that exploit chemical energy gradients. Life is a thermodynamic phenomenon. It extracts useful work from the temperature gradient between a hot star and a cold universe. When the last stars go out, this gradient disappears. There is no longer a hot object irradiating a cold background. The universe approaches thermal equilibrium. Any life dependent on stellar energy would die with the stars. But what about life based on other energy sources? Adams and Laughlin speculated about the possibility of life in the degenerate era based on the tiny energy released by proton decay. If protons decay with a half-life of around 10 to the 34 years, then a sufficiently large white dwarf would release energy from proton decay at a rate sufficient to maintain a very faint luminosity. Could biology, or something analogous to biology, exist in the extreme cold and dark of the degenerate era, exploiting the energy of proton decay the way we exploit the energy of stellar fusion? The answer is deeply uncertain. The energy flux would be extraordinarily low, the temperatures extraordinarily cold, the timescales of any process extraordinarily slow by any current biological standard. But the laws of physics do not explicitly prohibit information processing and self-replication in such an environment. They simply make it very different from what we know. Freeman Dyson, the physicist who famously argued in a 1979 paper that life could potentially persist forever in a cooling universe by slowing its own metabolism and hibernating for increasingly long periods, explored the limits of life in cosmological futures. His analysis assumed a universe that was slowing in its expansion rather than accelerating, and later work incorporating dark energy showed that his eternally living beings would eventually be overwhelmed by the de Sitter temperature of the cosmological horizon. But the spirit of the inquiry, the question of whether intelligence is constrained to the brief, bright window of the stelliferous era or might find ways to persist into the darker eras, is a genuinely interesting scientific and philosophical question. If life does exist in the degenerate era, it is life in a universe so different from ours that the word life might not adequately capture it. A metabolism running on proton decay energy, operating at temperatures close to absolute zero, processing information at rates many orders of magnitude slower than the slowest biological process we know, existing in the profound dark between the cold stellar remnants of a universe whose bright era ended a quadrillion years ago. Such a being, if it had something like cognition, would have an entirely different relationship to time than we do. What we experience as a second, it might experience as a geological epoch. A human life would represent, to it, an interval shorter than the shortest unit of time it could meaningfully distinguish, and it would have been born, if the concept applies, into a universe so old that the stelliferous era, all 100 trillion years of it, would be ancient history, as remote from its experience as the Precambrian era is from ours. The degenerate era's possible inhabitants, speculative as they are, remind us that when we ask what happens after the universe ends, we are not just asking about physics. We are asking about the boundaries of what can think about what happens. Life, if it persists, changes the nature of the question. An observer in the late degenerate era, watching the last white dwarfs dissolve through proton decay, is not watching the universe end from a purely external perspective. The observer is part of the universe. The ending is also an ending of the observer's world, a context, a home. The question of what comes after is personal, in a way that purely physical questions are not. That personalization of the question, the sense that what happens after, matters not just as a physical fact, but as something that touches the observer's own existence, is something we share with any hypothetical mind in the degenerate era or the black hole era. The universe's temporal extent dwarfs any individual life by a factor too large to compute. But the individual life, looking out at the universe, knowing its own brevity, asking what comes after, is participating in something that the universe could not do without some arrangement of matter doing the asking. Whether that means anything is, as always, a question for another time. We began this journey with a night coming that makes all other nights seem brief. We end it with something quieter, the recognition that even in the perfect dark and the endless cold of what comes after everything, the laws of physics do not fully rest. Something hums, at the quantum level. Something fluctuates. Something, somewhere across the incomprehensible span of the universe's afterlife, assembles itself briefly from the void and dissolves again. The universe is not done surprising itself. It just does it very, very slowly. And if Penrose is right, one of those configurations does not dissolve. It becomes everything again. Every time a star burns out somewhere in the cosmos tonight, it is contributing to a future that extends further than any number we have named. Every photon released by every hydrogen atom in your body right now is participating in a process that began in the first seconds after the Big Bang. and will not be fully concluded until long after the last black hole has whispered out its final burst of Hawking radiation into a cold and empty expanding void. The universe is 13.8 billion years old and barely getting started. If this is your kind of journey, subscribe and be here for the next one. Leave a comment below with where in the world you are and what time it is. And thank you, sincerely, for spending your time in the vast and temporary light.